So we're going to get into actually visualizing the molecules now. So we're going to switch gears from stoichiometry and the sort of experiments we did with light and spectroscopy. And now we're going to get back into molecules and sort of trying to picture how they look in 3 dimensions. So we're going to be doing molecular structures. As far as the ALEX reports, good job. I think a lot of people have already started on tonight's homework. Like the weekend after a test, hey, props. Okay, that's really good. It'll pay off. You finish that exam and you just keep grinding, going and going. We can rest in the Christmas break. Okay, maybe a little break at Thanksgiving, but drive hard through the end of the semester, and things will turn out well for you. Okay, so this is the topics that are due tonight, and most of it's going to be covered today. I'm not going to go through like the ALEX. Like in the past, I would show the exact ALEX problem and do it, but there's a whole bunch of them. But I'm just going to teach you how to do Lewis dot structures, and that'll give you enough knowledge to just go through the ALEX ones real easy. So we'll start out with just the atoms. Here's an example ALEX problem. I started doing a few of them, and I was like, okay, these are like little nibbles, and I just want to teach you how to make Lewis dot structures. So we'll jump ahead. So it's saying draw the Lewis dot structure for a selenium 2- anion. And so these are the different things you have to do. You got the selenium, the atomic symbol. And so we find selenium in the periodic table. And the question is, how many valence electrons does it have? Okay, so it's over there. How did you find that so fast? You went to selenium and looked straight up. And in this table, you see the Roman numeral 6. On ALEX, it would be 6A, group 6A. That's the valence electrons. So I'm going to do 6 valence electrons here, plus 2 from the negative charge, right? Equals 8 total. So we draw the elemental symbol. We draw the 8 electrons around it. Don't forget the bracket and the charge. Okay, so that if it's charged, you put the bracket around it, and you put the charge up there in the corner. And in fact, all of the oxygen group, that's called the chalcogens. We had the halogens and the chalcogens and the pnictogens. Okay, so the chalcogens all have that same structure. And these are just the valence electrons. So that's why oxygen, sulfur, and selenium are isoelectronic in their valence electrons. So these are the electrons that are farthest from the nucleus, and that's going to govern the chemistry. So whenever these atoms are in space and they bump into each other, it's their valence electrons that are bumping into each other. And so that causes them to click together. Think of the valence electrons like the bumps on Legos, right? So when you bring Legos together, the 6 bump and the 6 bump can go together perfectly, okay? And you can sort of use the bumps to guide how you can hook things together. That's the way I think of it. That's why I loved Legos as a kid, and I love chemistry. To me, they're the same thing. The atoms are God's Legos, and they made everything in the whole universe with just 100 or so pieces. And I don't know about you, but I had way more than 100 different types of Lego pieces, and I could only make a few things. So these are much more versatile, and it's the valence electrons that allow these atoms to form all the different compounds that we have in the universe, which is amazing.
What if it didn't have the 2 minus?
Okay, good. So if it was just SE,
Just SE.
yeah, just SE, we could draw it a couple of different ways. And so we would have 6 valence electrons, and we would just put those around the molecule. So the way I do this is I get the electrons as far apart as possible first. And so I've used up 4 of them, and then I start pairing them up. And so that's what it would look like. So I just go around and I put them all on there. And again, there would be no bracket and no charge. And so I would just leave it like this. Yes. Not really, but that's how I do it. Yeah. And so you kind of see that you've got a couple of open spots for electrons here and here.
Would it be wrong if you did 3 pairs?
I think so, because here I want to see that there's an open spot here for something like a hydrogen. So a hydrogen comes in with a dot, and you could put a hydrogen over here. We're kind of getting ahead of ourselves, but we have this open spot here that dot can go into. And so this can form a bond. And this one can go here into that spot. And that's kind of what I was talking about, the Legos, how they snap together. The hydrogen has one dot, the selenium has a dot, and they line up with each other and can snap in. Okay.
You would need to draw the brackets where it begins to put.
Yeah, so we don't need the bracket or the charge because it's not charged. Yeah. And so this is your first bonding theory. The other one is molecular orbital theory, which I can't remember. I think we do get to that a little bit in this course. But anyway, this is our bonding theory, and so we'll call it two different things, but we mean the same thing: local bond theory or valence bond theory. Valence bond, you understand that word valence is the valence electron. So these are bonds formed by the valence electron. So that's why it's called valence bond theory. But I think local bond theory is more an appropriate name because we're saying that the electrons, the two electrons that form the bond, are local to the two atoms. So they are between the two atoms that they form the bond with. So these two electrons are between the bonded atoms, and that's the local part of local bond theory. So like what I just did with the selenium, and I had those two bonds with the hydrogen, the hydrogen brought in this electron and the selenium had the other one. You see that the hydrogen brought that electron in. We had pairs over here. And so these two electrons here form the bond. There's two electrons between the bonded atoms. And these two right here. So we're saying those electrons are local to that bond between the two atoms they're holding together. We would just pull away two electrons. Okay, so let me go ahead and do that one since you asked. So a selenium 2 plus would be, so we just start around here, 1, 2, 3, 4. It had 6 minus, so we had a 2 plus cation. So we lost 2. So I would keep all of those electrons unpaired, and it would be ready to bond to 4 things. We call these over here, these pairs of electrons that aren't bonded to anything, we call these lone pairs. I don't know why I put an E there, lone pairs. And then we had this 8-electron noble gas configuration. We know that's unusually stable. And so then we have this, let me see if I can get the different color here. Okay, so these are covalent bonds, and so they get to they get to share these electrons. And so when selenium is looking around, it sees 8 electrons in its electron cloud because it's sharing 2 of those with hydrogen. But it gets to claim those 8 electrons, and it has now the noble gas configuration of argon. And the hydrogen is happy because they're sharing. So the hydrogen gets to see 2 electrons, and it has the noble gas configuration of helium. So that's what makes these covalent molecules so stable, is because instead of like ionic bonding, where chlorine and sodium get together, chlorine steals the electron from sodium, and it has the noble gas configuration of argon, and sodium lost its electron, so it's dropped back around noble gas configuration of neon. And then it's just the charged particles that are attracted to each other, but they're attracted in all directions. So this sodium in a sodium chloride crystal is surrounded by chlorides, and so it's attracted to all of those chlorides, and you couldn't even say which one of those it's bonded with because it's not directional bonding. So ionic bonding is not directional at all. It's positive and negative charges just stuck in a crystal. And it's ionic because you've stolen electrons, and now the chlorine has sodium's electron. It's not sharing at all. So it's a chloride minus and a sodium cation, sodium plus. And you make a crystal by just stacking the negatives and positives next to each other. Covalent bonding is way different. These molecular compounds like this H2SE, notice there's directional bonding. That selenium is bonded to that hydrogen, and if it was in a crystal with other selenium hydrogen molecules, it really wouldn't be bonded to those. It would be bonded internally to those hydrogens and then just sort of stuck in a crystal lattice with the others. So the stability of the molecules will have many atoms that have an 8 electron nearby. So that's why I'm counting up this as 8 here, 8 electrons, and it's very much like krypton. And then the sodium, or this hydrogen, has 2 electrons, which is very similar to helium. So they're very happy. They have their noble gas cores. Now this idea of getting 8 electrons, obviously hydrogen doesn't get 8 electrons. It wants 2 because it wants to be like helium. But all of the second row, third row, those want to have 8 electrons to be like their noble gas cores. But the octet rule, this 8 electron rule, is most strongly adhered to by these 4 atoms. Okay. And so whenever we form double bonds, it's probably because we have some of these atoms on here. So this drives double bonds. So whenever you have a molecule with double bonds, it's being driven by the carbon, the nitrogen, the oxygen. Probably not the fluorine. Fluorine is just going to make 8 electrons around itself, but certainly CN and O. And in elements above period 2, so the third row and below, with phosphorus and sulfur and so on, those can bond to more than 4 things and can have more than 8 electrons around them. So let's look at simple Lewis dot structures. We've already drawn some. So think of, again, like Legos. This is compatible. We can form a bond with 2 electrons, and the hydrogens each have 1. And so when they form that bond, they have that nice shared electron. Each one of those hydrogens feels like helium because helium has its 2 electrons, and they're very happy. Chlorine, again, if you draw the Lewis dot structure just for a chlorine atom, so chlorine comes in with 7 valence electrons, 7 VE. So I'm going to draw 1, 2, 3, 4, 5, 6, 7. And so see, I've gone all the way around a couple times, and I've stopped short of filling it up with 8 because it only has 7 valence electrons. But it has this huge open hole here for another electron. So chlorine can bond very easily, make a single bond with anything that has a single electron that can donate to it. So you can get 2 chlorines together and make this Cl2 molecule, and each of those chlorines feels like argon now because it gets to share those electrons. Now, one thing that we will do is we will not draw all the dots in the middle. So look at these dots here in the middle. Those have been replaced with a dash. So each one of those dashes equals 2 electrons. So if we're counting up electrons around this molecule, we could see on the lone pair side, we have 2, 4, 6, 8, 10, 12, 10 or 12 non-bonded electrons. And then here in the middle with that dash, we have 2 bonded electrons. So 2 electrons are contained inside a bond. Here's some other simple Lewis dot structures from the second row, first and second rows. Okay, so we could count up all the electrons. Let's do this ammonia molecule. So how many electrons do we have total in the molecule? Well, we've got 2 here, 2 for each of the bonds. 2, 4, 6, 8. So we have 8 electrons total. Same for the methane, 2, 4, 6, 8. We have 8 electrons here. For water, we have 2 lone pairs and 2 bonds, and so we have 8 also there. For fluorine, we've got 6 on the fluorine that are non-bonded and 2 in the bond, and so we have 8. So with this octet rule around those bigger atoms, all of those, the fluorine, the oxygen, nitrogen, carbon, they all feel like neon because they have access to 8 electrons. So here's another Alex question. Alex gives you a Lewis dot structure without the dashes. It just gives you the dots, okay, and asks you to categorize the different electrons. And so these are the Alex questions. You have bonding pairs, and so it's calculating pairs. And so here's a pair of electrons that's bonding. So that's one bonding pair, and then these are the lone pairs. There's 3 of those. But today, when I'm teaching you Lewis dot structure, I'm going to be asking you to count electrons a little different way. I just want you to count up electrons, not pairs, okay? This is really the electrons that are important. So count up individual electrons. And so if we're looking at this, the number of bonding electrons would be 2, and the number of non-bonding electrons would be 6, okay? Does everybody agree with that? Yeah. So again, the pairs, there's 3 pairs, so that's 6, and there's 1 pair, that's 2. Okay. All right. So let's draw some Lewis dot structures. So this morning we're just going to practice drawing Lewis dot structures, and next time too. So we're going to draw all kinds of Lewis dot structures for 2 lectures. So this is my procedure for doing the Lewis dot structures. It's similar to what's in the book, but there's some specific things that I want you to do. So we're going to sum the valence electrons. So if I say draw the Lewis dot structure for ammonia, NH3, then you got to add up all of the valence electrons, not just from the nitrogen, but also from the 3 hydrogens. So we add up all of the electrons, and that's the number of electrons total. So in tot, that's the total number of electrons. Then we're going to create single bonds. So we're going to put the first atom in the middle and surrounded by the other atoms, and we're going to draw single bonds with everything. And then we're going to subtract out those bonded electrons. So we subtract 2 electrons for every single bond. Those are the number of bonded electrons. And then we're going to replace the non-bonded pairs of electrons on the most electronegative atoms first. And we're going to learn about electronegativity today. And then we subtract these non-bonded electrons from the total. And if there's any electrons remain, we're going to add them to the central atom. And then we're going to form double bonds to give an octet for carbon, nitrogen, oxygen, and fluorine. And then optional, this will be something we do next time, is we're going to compute the formal charges. And then later in the semester, we're going to generate 3D structures using Vesper theory. So this is the full thing. You can put a star on this page in your notes so you can come back to it if you ever need to review this procedure. So now let's put this procedure into practice. So we're going to make our molecules, and then we're going to, sometimes we need to make double bonds. And so here's an example of carbon and oxygen forming a double bond. And we'll see examples of that when we draw them. But I just wanted to put this little screenshot of what's in the book here, so it talks about double bonds. We'll see this when we go through our procedures. Okay, so let's practice. So here's our water molecule. Let's start with that one. So let's add up the total electrons. Okay, so in total is equal to 2 times 1. All right, so we have this 2 here. There's 2 hydrogens. And each hydrogen, the valence electrons for hydrogen are 1. They're in the periodic table. Plus 6 for the oxygen. So we have 8 total electrons. So then the next step for our procedure was draw the big atom in the middle and surround it with smaller atoms with single bonds. So we're going to create a sort of a single bond molecule. So HOH. And then we count up the number of bonded electrons and we subtract those. So minus 4 bonded electrons. So once we do that subtraction, we have 4 electrons left. And so then we put those on the more electronegative atom, and electronegativity is highest in that corner. So that's a way to kind of gauge how much atom wants electrons. And so fluorine wants electrons the most. Oxygen really wants them too. Hydrogen's way over here, so it doesn't want electrons very much. And so we've got 4 electrons to put on this molecule, and there's a big fat oxygen saying, give me more. And also oxygen wants 8 total. It's already got 4. So let's put the other 4 on that oxygen. 1, 2, 3, 4. And so we subtract those from our total. So these are the non-bonded electrons, NBE, and we get down to 0. So we're done. So we just keep track of our electrons. We come up with the total, we make bonds, we subtract the bonds, then we have some left over, and then we make non-bonded electrons and subtract those, and then we hopefully get to 0. If we have electrons left over here instead of 0, then we would stick more on the central atom. Okay. Let's do ammonia. So here's a nitrogen. How many valence electrons for nitrogen?
5.
Yeah, good, 5. And then plus 3 times 1 for the hydrogens. And we have 8 again. Yay. Okay. These small molecules on the second row are easy. All right, so then the first thing we do is we make a single bonded network around the heavy atom, that nitrogen. We're going to put it down first. So we've made 3 bonds, so that's 6 bonded electrons. We subtract those from our total. So we have 2 left over, and so we're going to put a lone pair on that nitrogen. Okay. Minus 2 non-bonded electrons, we get down to 0. That tells us we're done. All right. We're starting out easy. So if this is looking easy, good. You should let yourself get it. Let's do this whole series of halogens. Okay. So total, we have 1 for the hydrogen plus 7 for the fluorine equals 8. And we're going to make the HF, single bond. That's minus 2 bonded electrons. So we have 6 left over. And so we're going to put those on that heavier atom, the fluorine. 6 non-bonded electrons, and we're down to 0. Now, you don't have to do this whole long procedure after you get good at it, okay? And so can you imagine that HCl is exactly the same? Because chlorine has 7 valence electrons. HBr is the same because bromine has 7 valence electrons. And even iodine has 7. So we ought to be able to just write those out without doing all the math. So this is HCl. 1, 2, 3, 4, 5, 6. This is HBr. And these molecules exist just in this form. So, this local bond theory is giving us something that is pretty universal. I can go along and I can predict the structure of HI or HBr or any of these. So that's pretty nice. In fact, let's go over here and let's do pH 3. So where's phosphorus? It's right below nitrogen. So it's going to look the same. pH, H, and 2 non-bonded electrons. Isn't that nice? Again, so that's why we talk about valence electrons so much, because it's so useful. If I know NH3, I also know pH 3, and I also know ASH3, although I don't know if that exists, but it could exist. Yeah. And then methane. Okay, let's do that one. So the carbon has 4 valence electrons, plus 4 times 1 for the hydrogens. Okay, so we end up with 8 total. So we put that carbon in the middle and we put 4 bonds around it, and there's 2 electrons for each. So the -8 bonding electrons. And so we're down to 0, so we're done. Okay, there's surely somebody has a question or something that I can clarify. Okay. I'll give you a minute.
I assume I have to go over like if it's like nitrogen and chlorine. Here in a sec, right?
Say that again.
Like what if it was like nitrogen and chlorine, everybody?
Okay, that's good. Let's do nitrogen and chlorine. So let's see what's next. Okay, we'll do double bonds next, but let's do the end. So the question was, well, I guess the observation too is all these are with hydrogen. What if we do something other than hydrogen? Okay, so let's do. I'm going to erase this nitrogen one down here so I get some more room. Okay, let's go for broke and let's do NCl3. All right, so we've got a lot here. We got the number of valence electrons total is equal to 5 from the nitrogen plus 3. That's the subscript here, and then chlorine has 7. Okay, so 3 times 7 is 21, and then we add 5 more, so we got 26. Is that correct? When I'm doing math in front of 60 people, I make silly mistakes. Okay, so 26 total. All right, so then we put that, we typically pick, like if it's NCl3, I mean, this is sort of telling you that nitrogen is the central atom and the chlorines are all around it. Okay, so we're going to put the nitrogen in the middle, and we're going to make single bonds. So it looks just like ammonia, but it's got Cl's on there. And how many electrons have we used up out of our total? Right, 2, 4, 6. So -6 bonding electrons. So we have 20 left. All right. So the next step in our procedure was to put them on the more electronegative atom first. So we look up there and we see chlorine is closer to fluorine. It's to the right of nitrogen. And so it should want those electrons more than the nitrogen. So we're going to put them there first. And we're going to fill up. We're going to make sure each chlorine has 8. So it's already got 2. So we're going to put 6 on each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I'm just going to subtract those 18, and I've got 2 left. And then if I've got any left after that, I put them on the central atom. And so we're going to put those 2 on the nitrogen, and we're down to 0. So that's the Lewis dot structure for NCl3. Anything trip you up in that procedure? Yes. Let's see what would happen. Before we try that, let me just show you, if you look at the atoms, let's say we draw let's think of it as sort of a Lego, okay? So let's draw the nitrogen Lewis dot structure. So nitrogen has 5 electrons, right, valence electrons. So 1, 2, 3, 4, 5. And so we're looking at this nitrogen and just begging for 3 bonds. So that's another way to think that the nitrogen's in the middle and the chlorines are snapping on. And if we draw the chlorine by itself, so we have Cl, and it has 7. So 1, 2, 3, 4, 5, 6, 7. And so it's got the 1 dot that can snap to the nitrogen. And so if you're looking at just the atoms, you see how they fit together and they will snap that way. So that's why these guys would form the bond. And then you do the same thing with the chlorine below and the other. So I'm not exactly sure how I would write the chlorine in the middle and have the nitrogen on the outside because of the way the dots fit. Yeah, so it's a good question, but that's looking at the valence electrons for nitrogen, you see that it has 3 spots open for bonding. And we'll notice that nitrogen wants to bond for 3 things, carbon wants to bond with 4 things. So the carbon is coming along and it's got 4. 1, 2, 3, 4. So it's open for 4 bonds. And so I could make carbon tetrachloride 1, 2, 3, 4, 5, 6 with an extra here. And so this can form a bond here, and I can do that 4 times for carbon, and sure enough, CCl4 is a common molecule. So it snaps 4 chlorines around it. Let's try double bonds now. So yeah, we've got some time. Okay. I don't want to run out of time because I'm... All right, so here's oxygen. There's 2 times 6. So we have 12 total electrons. All right, so I form a single bond. I've got 10 left over. Okay, it's oxygen, so they're gonna equally share these electrons. So we're gonna start doing pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, I'm out of electrons, and I've got a spot for 2 more over here. So this oxygen has 8. Let me change color so I can count them up. Okay, so if I draw these circles, you see how this oxygen has 8 available. Does everybody see that? Let me see nods. Yeah. Okay, and this one only has 6. So, you know, to quote a little kid, that's not fair, right? These are they're twins, they're oxygen, and this one with 6 is pissed, okay? I want 2 more electrons. So one way to do that as a parent is to say, okay, share 2 more. You with 8 can share 2 more. And so they're going to share 2 more and make a double bond. So this is the Lewis dot structure of oxygen. It's got a double bond. And it doesn't really matter how you draw the dots. So that's the Lewis dot structure for oxygen, O2. And now each of these molecules can count nearby, can count 8 electrons. Because it's covalent. So these electrons in the middle are in the valence of both atoms. So both atoms get to count them. So both atoms have 8. You see how the double bonds allow an octet for both oxygens. Okay, so that's why we form double bonds or triple bonds in the case of nitrogen. Let's do nitrogen now. So we have 2 times 5. So we have 10 electrons. Start with a single bond. All right, so we have 8 left over. And so I can put 1, 2, 3, 4, 5, 6, 7, 8. Well, now this nitrogen is really deficient. He's only got 4 that he can claim. The other one has 8. That's not fair. So we're going to make 2 more bonds. We're going to share 2 more groups of electrons to make a triple bond. So this nitrogen, when it shares more electrons, it doesn't lose anything. It has 8, it can still claim 8, but the other one gains because, again, the other one's sharing with it. So we'll make this molecule look like this with a triple bond. And I just put the lone pairs as far apart as possible. So that's why I scooted them out to the outside. Okay, so that's nitrogen. Why it's such a stable molecule. If you think about it, our bodies, we're breathing in 80% nitrogen all the time, and it's not doing anything in our bodies. It's really chemically inert. So our bloodstream is saturated with nitrogen. It's in our brain, it's in our body, but that triple bond is super strong. It's not very reactive. So it's just an inert gas. Okay. And so it's the oxygen that's reactive. It reacts with the metal in our hemoglobin, and then that provides oxygen for the combustion reactions that are going on in our bodies to give us energy. So that's a little bit about nitrogen. Super good gas, super inert gas, and so it's great. Okay, let's do CO2, something with a little bit more interesting structure. So let's add them up. We got 4 valence electrons for the carbon, plus 2 times 6 for the oxygen. So 2, and the oxygen is 6. Okay, 2 times 6 is 12, plus another 4 is 16. All right, let's make single bonds first. Put the carbon in the middle, and the oxygen's on either side. We've used up 4 electrons, and so we've got 12 left. And we're going to put them on the most electronegative atom. Which one is that? Oxygen. It's closer to the corner. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're down to 0. We've finished putting our electrons on the molecule. But poor old carbon does not have an octet. It can only claim 4 electrons. And so it's asking the oxygen, hey, share a couple with me. So this one shares 2, this one shares 2. And so then we have the structure of CO2, which has a double bond to each oxygen. And I like to draw my lone pairs kind of at 120 degree angles like this. So what do I mean? Well, it's like this little lone pair cloud is out here, kind of like a Mickey Mouse ears. Okay, and this is 120 degrees, and this is 120 degrees, and this is 120 degrees. So a third of the way around. It's just, again, electrons hate each other, so let's get them as far apart as possible. Okay, so that's CO2. Now, does that make sense from a carbon standpoint, an oxygen standpoint? Well, yeah, it does. If you were to look at carbon, it's got 1, 2, 3, 4, and you got an oxygen over here. Let's draw it like this. So it's got an empty spot for 2 electrons, and these 2 electrons could go right there into that spot and form a single bond, and then these 2 could come down and double bond with it too. So again, it'll click together, similar to what we've done with the nitrogen and the chlorine. Now this is a new molecule, new type of molecule. Notice it's not a binary molecule or homonuclear diatomic. We've got 3 atoms on here, so let's figure this out. So we got 4 for the carbon, plus 2 times 1 for the hydrogens. Again, there's 2 there. The hydrogen is 1 valence electron each, plus oxygen is 6. So that ought to equal 12. We know hydrogen's not going to be in the middle, right? Because hydrogen only bonds to one thing. So hydrogens are going to be stuck on the ends of things, okay? So carbon is listed first. Let's put that in the middle. That turns out to be right, okay? So let's put carbon in the middle. I'm going to draw this up like this. So an oxygen up and a hydrogen down and a hydrogen down. And so I've used up 6 electrons, minus 6 bonding electrons, and I've got 6 left over. So they go on which atom? These 6 leftover electrons. Yeah, y'all are fast with that. It's more electronegative. It's more in the corner than carbon, and so it's going to want those electrons first. So we go 1, 2, 3, 4, 5, 6. And then we evaluate. Do we have an octet for carbon, nitrogen, oxygen, fluorine? Oxygen does. It's got 8 electrons, but carbon doesn't. How many valence electrons can carbon claim right now? Say it on 3. 1, 2, 3. So the carbon has how many bonds? 3. And how many electrons in each bond? 2. So it can claim 6 valence electrons. So that's not 8. It doesn't have an octet. So carbon wants electrons. It needs 2 more so it can feel like it's neon. So carbon wants to feel like neon, which means it wants 8 electrons. So it's going to ask the oxygen, can you share 2 more? And oxygen doesn't care because sharing is fine. Okay, and so then this is what we end up with. A double bonded to oxygen. Oxygen now has 2 lone pairs. I'm going to put those at 120 degrees angles, and I'm going to put these hydrogens also at 120 degrees. So that's formaldehyde, the compound formaldehyde. So they used to preserve, animal species in formaldehyde in the biology labs. They stopped using it because it's a carcinogen. There was also the molecule for one of the first plastics ever made, so Bakelite, where they polymerized formaldehyde. So, now, what if you were to, well, I don't know. I mean, you could draw formaldehyde a different way, but this is the correct way. So, okay. Oh, I was going to do some with big ones. This is kind of a copy paste error. I didn't change the molecules, but let's do one that's crazy big. Okay, let's do. Let's go for broke and do SF6. So sulfur hexafluoride. So sulfur has 6 valence electrons. And then we have 6 fluorines that each have 7. Okay. So that's 42 plus 6, so 48. Did I do that right? 48 total electrons. So the sulfur we're going to put in the middle. And we got to draw 6 fluorines around this guy. So 1, 2, 3, 4, 5, 6. All right, so 6 single bonds. How many electrons is that? 12. Okay, so we subtract 12 bonded electrons. 6 there. So we have 36 left. And we've got 6 fluorine atoms. So we can put 6 each on all of that. So bear with me. So we got a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So that's sulfur hexafluoride. And now we can make that with sulfur because it's on the 3rd row, but we can't make oxygen hexafluoride. The 2nd row atoms are not big enough to have 12 valence electrons. So look at sulfur, it's a hog. It does not have the octet rule for sulfur. It's got 12 valence electrons around it because it's so big, and that's okay. So row 3 on down, you can have some really big central atoms that have lots of things around it. But you can't do oxygen hexafluoride. Oxygen's just too small. The fluorines try to get too close and they bump into each other and they won't stick to the oxygen. Okay. So that's the big one. Okay. Let's do the same thing, but with can I get you to close that? Let's do PCl5. Okay, so we have 5 valence electrons for the phosphorus, plus 5 times 7 for the chlorine, 5 times 7. So that's 35 plus 5, that's 40. All right, so we put the phosphorus in the middle, and then 1, 2, 3, 4, 5 chlorines around it. So we've used up 10 electrons. So we have 30 left. So 10 bonded electrons, 30. And so if you look at that, we've got 30 divided by 5, so that's going to be 6 on each. So 1, 2, 3, 4. I won't count them all. I'll just do it. So if you look at this, notice the trend. Phosphorus has 5 valence electrons. What's the maximum thing it can bond with? 5 chlorines, right? Sulfur has 6 valence electrons. What's its max valence? 6 things, okay? And so then we get to carbon. What do we see? Carbon or silicon. Again, the 4 valence electrons, maximum thing it's going to bond with is 4. It just doesn't have any more electrons to share. So the nitrogen, or let's do the phosphorus, you know, we would draw it like this. Oops, sorry. And no, this is the last comment and we'll finish up. You know, this is what we would typically draw, but in this case, it's those, there's no pairs. It's like 5 individual electrons around the phosphorus. And so it can bond with those 5 things with those single electrons sticking out there.
Would it be the same thing for like SE? You could bond to 6.
Yeah, SE could bond to 6 things. Yeah. And a lot of times that's how we get metals to fly, like become gases, is we'll take a metal and we'll stick fluorines around it. And so like the uranium enrichment process that we used and that Iran's using now with their centrifuges, they have uranium hexafluoride. And so it's very similar to the sulfur hexafluoride. They have a uranium atom and fluorines all around it. And those fluorines hate each other, so it's a gaseous molecule. So you got uranium in the gaseous state so that you can separate it. So.